Dear students, as we are progressing in the stream of learning under the chapter Current Electricity, it becomes important for us to know and understand the Kirchhoff's laws. In 1842, Kirchhoff put forward his two laws to solve complicated circuits. Kirchhoff ਦੇ ਇਹ laws ਸਾਨੂੰ complicated circuits ਵਿੱਚੋਂ flow of current ਸਮਝਣ ਵਿੱਚ ਮਦਦ ਕਰਨਗੇ। ਇਹਨਾਂ laws ਦੀ ਜਾਣਕਾਰੀ ਅੱਗੇ ਆਉਣ ਵਾਲੇ ਕੁਝ topics ਨੂੰ ਘੱਟ ਗੁੰਝਲਦਾਰ ਅਤੇ ਆਸਾਨ ਬਣਾਉਣ ਵਿੱਚ ਵੀ ਸਹਾਇਤਾ ਕਰੇਗੀ। ਆਓ ਪਹਿਲਾਂ ਅੱਜ ਦੇ ਪਾਠ ਦੇ learning objectives ਜਾਣ ਲਈਏ।
After the completion of this topic, the students will be able to state and describe Kirchhoff's laws, describe the Wheatstone bridge and explain its principle, describe slide wire bridge.
Kirchhoff ਦੇ ਦੋ laws ਹਨ। ਆਓ ਫਰਸਟ law ਤੋਂ ਸ਼ੁਰੂ ਕਰਦੇ ਹਾਂ। ਇਸ ਨੂੰ Kirchhoff's junction law ਜਾਂ Kirchhoff's current law ਵੀ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਇਸ law ਦੇ ਅਨੁਸਾਰ the algebraic sum of the currents meeting at a junction in a closed electrical circuit is zero. Kirchhoff's first law supports law of conservation of charge. This is because a point in a circuit cannot act as a source or sink of charge. Let me illustrate the meaning of this statement. Consider a junction O in the electrical circuit at which the 5 conductors are meeting. Let I1, I2, I3, I4 and I5 be the currents in these conductors in directions as shown in the diagram. We are required to adopt a sign convention. The current flowing in a conductor towards the junction is taken as positive, and the current flowing away from the junction is taken as negative. Then, according to Kirchhoff's first law, at junction O, minus I1 plus minus I2 plus I3 plus minus I4 plus I5 is equal to 0. Or minus I1 minus I2 plus I3 minus I4 plus I5 is equal to 0. Or sigma I is equal to 0. This is Kirchhoff's first law or Kirchhoff's current law. I will now like to show you a visual to give you a better perception of this law.
This is Gustav Kirchhoff, who introduced two laws for solving electric circuits. You can see a piece of wire being joined to another. Junction दो wires ਦੇ meeting point ਤੇ ਬਣਦਾ ਹੈ। Junction rule ਦੇ ਅਨੁਸਾਰ incoming currents ਅਤੇ outgoing currents ਦਾ ਜੋੜ 0 ਦੇ ਬਰਾਬਰ ਹੁੰਦਾ ਹੈ। ਧਿਆਨ ਨਾਲ ਦੇਖੋ, ਕਰੰਟ ਜੰਕਸ਼ਨ ਦੇ ਇੱਕ ਐਂਡ ਤੋਂ ਐਂਟਰ ਕਰ ਰਿਹਾ ਹੈ ਅਤੇ ਜੰਕਸ਼ਨ ਦੇ 3 ਹਿੱਸਿਆਂ ਵਿੱਚ ਵੰਡ ਹੋ ਕੇ ਤਿੰਨੇ ਆਰਮਸ ਵਿੱਚੋਂ ਫਲੋ ਕਰ ਰਿਹਾ ਹੈ। ਇੱਥੇ ਸਾਈਨ ਕਨਵੈਨਸ਼ਨ ਦੇ ਮੁਤਾਬਿਕ ਇਨਕਮਿੰਗ ਕਰੰਟ ਦਾ ਸਾਈਨ ਪੋਜ਼ਿਟਿਵ ਮੰਨਿਆ ਗਿਆ ਹੈ ਅਤੇ ਪਲੱਸ I1 ਨਾਲ ਦਰਸਾਇਆ ਗਿਆ ਹੈ। ਇਸੇ ਤਰ੍ਹਾਂ ਆਊਟਗੋਇੰਗ ਕਰੰਟ ਦਾ ਸਾਈਨ ਨੈਗੇਟਿਵ ਹੈ ਅਤੇ ਮਾਈਨਸ I2, ਮਾਈਨਸ I3 ਅਤੇ ਮਾਈਨਸ I4 ਨਾਲ ਦਰਸਾਇਆ ਗਿਆ ਹੈ। ਹੁਣ ਜੰਕਸ਼ਨ ਰੂਲ ਦੇ ਅਨੁਸਾਰ ਇਨਕਮਿੰਗ ਕਰੰਟਸ ਅਤੇ ਆਊਟਗੋਇੰਗ ਕਰੰਟਸ ਦਾ ਜੋੜ 0 ਦੇ ਬਰਾਬਰ ਹੋਣਾ ਚਾਹੀਦਾ ਹੈ। That is, sigma I incoming plus sigma I outgoing is equal to 0. Or I1 plus minus I2 plus minus I3 plus minus I4 is equal to 0. or the sum of all the incoming and outgoing currents at the junction is 0. Let us try to understand this by a simple analogy. Let there be water flowing through a huge pipe. At a certain point, the pipe gets divided into two parts. What do you think will happen to water flowing through it? Let us understand the water through the pipe before it's dividing as equal to the incoming current I1. The water gets divided into two parts, namely I2 and I3, representing the outgoing currents. You will agree to understand that the amount of water coming towards the junction is equal to the amount of water going outwards from the junction. This example very well symbolizes Kirchhoff's first law.
The second law of Kirchhoff is likewise known as the Kirchhoff's second law or Kirchhoff's loop law or Kirchhoff's voltage law. It states that the algebraic sum of changes in potential around any closed path of electric circuit or a closed loop involving resistors and cells in the loop is 0. That is, sigma delta V is equal to 0. It means, according to Kirchhoff's second law, in a closed loop, the algebraic sum of the EMFs and algebraic sum of the product of current and resistance in the various arms of the loop is 0. Kirchhoff's second law supports the law of conservation of energy. That is, the net change in the energy of a charge after the charge completes a closed path must be 0. In fact, Kirchhoff's second law follows from the fact that the electrostatic force is a conservative force and work done by it in any closed path is 0. To understand the meaning of this law properly, consider a closed electrical circuit as shown in this figure containing two cells of EMFs E1 and E2 and three resistors of resistances R1, R2 and R3. We are expected to follow a sign convention again. If a closed path of a circuit is traversed in clockwise or an anti-clockwise direction, then number 1, the EMF of a cell is taken negative if one moves in the direction of increasing potential, that is, from negative pole to the positive pole through the cell, and is taken as positive if one moves in the direction of decreasing potential, that is, from positive pole to negative pole through the cell. It means that while traversing a loop, if negative pole of the cell is encountered first, then its EMF is negative, otherwise positive. At second number, the product of resistance and current in an arm of the circuit is taken positive if the direction of current in that arm is in the same sense as one moves in a closed path, and is taken negative if the direction of current in that arm is opposite to the sense as one moves in a closed path. Let us apply Kirchhoff's second law to the closed path ABEFA. We then have I3R3 plus I1R1 minus E1 equal to 0, or E1 is equal to I1R1 plus I3R3. Similarly, for closed path ABCDEFA, we have E2 minus I2R2 plus I1R1 minus E1 equal to 0, or E1 minus E2 is equal to I1R1 minus I2R2, or sigma E is equal to sigma IR. Please keep in mind that this relation is true when there is no capacitor in the circuit. In the presence of a capacitor, this relation is not correct. Let me show the Kirchhoff's second law or Kirchhoff's loop's law through a visual.
You can all see a simple closed loop that consists of a cell connected to a resistor through a closed key, and the current flows through the loop. The energy in the circuit is conserved as the current starts from the positive terminal of the cell and gets back into its negative terminal. If E be the EMF of the cell, small r be its internal resistance, and capital R be the resistance of the resistor, then we know that summation over E minus IR plus summation over I into capital R is equal to 0. ਜੇ ਸੈੱਲ 9 ਵੋਲਟਸ ਦਾ ਪੋਟੈਂਸ਼ੀਅਲ ਡਿਫਰੈਂਸ ਸਪਲਾਈ ਕਰਦਾ ਹੈ ਤਾਂ ਲੂਪ ਰੂਲ ਦੇ ਅਨੁਸਾਰ ਐਕਸਟਰਨਲ ਰੈਜ਼ਿਸਟੈਂਸ ਦੇ ਅਕ੍ਰੋਸ ਵੋਲਟੇਜ ਡ੍ਰੌਪ -9 ਵੋਲਟਸ ਹੋਣਾ ਚਾਹੀਦਾ ਹੈ। ਇਹ ਵੀ ਕਿਹਾ ਜਾ ਸਕਦਾ ਹੈ ਕਿ ਸਰਕਿਟ ਵਿੱਚ ਵੋਲਟੇਜ ਰਾਈਜ਼ ਅਤੇ ਵੋਲਟੇਜ ਡ੍ਰੌਪ ਬਰਾਬਰ ਹਨ। ਆਓ ਇੱਕ ਐਨਾਲੋਜੀ ਦੇਖੀਏ। ਵੋਲਟੇਜ ਰਾਈਜ਼ ਅਤੇ ਵੋਲਟੇਜ ਡ੍ਰੌਪ ਨੂੰ ਇੱਕ ਡਬਲੀ ਸਲੋਪਡ ਸਰਫੇਸ ਨਾਲ ਰਿਪਰੈਜ਼ੈਂਟ ਕਰਦੇ ਹਾਂ। ਇੱਕ ਬੰਦਾ ਸਲੋਪ ਦੇ ਇੱਕ ਐਂਡ ਤੇ ਖੜਾ ਹੈ। ਜੇ A ਅਤੇ B ਸੈੱਲ ਦੇ ਟਰਮੀਨਲਸ ਹਨ ਤਾਂ ਬੰਦੇ ਦੀ ਸਾਈਡ ਤੋਂ ਸਰਫੇਸ AB ਦਾ ਰਾਈਜ਼ਿੰਗ ਐਂਡ ਰਾਈਜ਼ ਇਨ ਪੋਟੈਂਸ਼ੀਅਲ ਬਾਈ ਦੀ ਸੈੱਲ ਰਿਪਰੈਜ਼ੈਂਟ ਕਰਦਾ ਹੈ। ਇਸੇ ਤਰੀਕੇ ਨਾਲ ਜੇ C ਅਤੇ D ਐਕਸਟਰਨਲ ਰੈਜ਼ਿਸਟੈਂਟ ਦੇ ਟਰਮੀਨਲ ਹਨ ਤਾਂ ਬੰਦੇ ਦੀ ਆਪੋਜ਼ਿਟ ਸਾਈਡ ਤੋਂ ਸਰਫੇਸ CD ਦਾ ਫਾਲਿੰਗ ਐਂਡ ਪੋਟੈਂਸ਼ੀਅਲ ਡ੍ਰੌਪ ਰਿਪਰੈਜ਼ੈਂਟ ਕਰਦਾ ਹੈ। ਜਿਸ ਤਰ੍ਹਾਂ ਬੰਦਾ ਸਰਫੇਸ AB ਤੇ ਚੜ੍ਹਦਾ ਹੈ ਉਹ ਪੋਟੈਂਸ਼ੀਅਲ ਐਨਰਜੀ ਗੇਨ ਕਰਦਾ ਹੈ। ਅਤੇ ਸਰਫੇਸ CD ਤੋਂ ਉਤਰਦਿਆਂ ਪੋਟੈਂਸ਼ੀਅਲ ਐਨਰਜੀ ਦਾ ਇਕੁਅਲ ਅਮਾਉਂਟ ਲੂਜ਼ ਕਰਦਾ ਹੈ। Also, there is no change in his potential energy as he walks back to the starting point along the base of the double slope.
Though both of the Kirchhoff's law talk about the complicated circuits, can you find some differences between them? Let me help you finding these differences out. Just look at this table. First law supports the law of conservation of charge, whereas second law supports the law of conservation of energy. According to first law, sigma I is equal to 0, while according to second law, sigma E is equal to sigma IR. Then the first law can be used both in open and closed circuits, while the second law can be used in a closed circuit only. Students, whatever laws and rules we study in physics are supposed to make things easier at some or the other level. The laws and rules are generally applied to benefit us, either in everyday life or for some scientific purpose only. The Kirchhoff's laws that we have learned today are also used and applied to a number of scientific devices. Let us now get to learn some of these applications. We will start with a Wheatstone bridge. The principle of Wheatstone bridge states that if four resistances P, Q, R and S are arranged to form a bridge as shown in this figure with a cell E and a one-way key K1 between the points A and C and a galvanometer G and tapping key K2 between the points B and D. On closing K1 first and K2 later on, if galvanometer shows no deflection, then bridge is balanced. In that case, P upon Q is equal to R upon S. Let us prove this mathematically. Let I be the total current given out by the cell. On reaching the point A, it is divided into two parts. I1 is flowing through P and I minus I1 through R. At B, the current I1 is divided into two parts, Ig through the galvanometer G and I1 minus Ig through Q. The current Ig through the arm BD and I minus I1 through AD combine to send a current I minus I1 plus Ig through S. On reaching the point C, the current I minus Ig through BC and I minus I1 plus Ig through DC combine to give total current I, hence completing the circuit. The values of the currents at a junction can be verified by applying Kirchhoff's first law at that junction. Applying Kirchhoff's second law to the closed circuit ABDA, we get I1 into P plus Ig into capital G minus of I minus I1 into R equal to 0. We will name this as equation 1, where capital G is the resistance of galvanometer. Again, applying Kirchhoff's second law to the closed circuit BCDB, we get I1 minus Ig into Q minus I minus I1 plus Ig whole into S minus Ig into capital G equal to 0. This is equation 2. The value of R is adjusted such that the galvanometer shows no deflection, that is, Ig is equal to 0. Now, the bridge is balanced. Putting Ig equal to 0 in equations 1 and 2, we get I1P minus of I minus I1 into R equal to 0, or I1 into P equal to I minus I1 into R. Let this become equation 3. We also have I1 into Q minus of I minus I1 into S equal to 0, or I1 into Q equal to I minus I1 into S. Let this become equation 4. If we divide equation 3 by equation 4, we get P upon Q is equal to R upon S. I am sure you will like to see the Wheatstone bridge circuit as well as its principle through a visual. So, look here.
You can see a Wheatstone bridge circuit here. As the current I starts to flow from the positive terminal of the cell at point A, it gets divided into parts I1 and I2 and flow through arms AB and AD respectively. At joint B, Ig, which is a small portion of current I1, is sent to pass through the galvanometer, and the galvanometer shows a deflection. The currents rejoin at the joint C and flows back to the negative circuit terminal of the cell via the closed key. The resistances are adjusted so that the galvanometer shows no deflection. This is known as the balanced condition of the Wheatstone bridge. At this stage, the relation between the resistances of the four arms of the circuit is P upon Q equal to R upon S.
ਹੁਣ Wheatstone bridge ਦਾ ਪ੍ਰਿੰਸੀਪਲ ਅਤੇ ਇਸ ਦਾ ਮੈਥਮੈਟੀਕਲ ਪ੍ਰੂਫ ਤੇ ਤੁਸੀਂ ਸਮਝ ਹੀ ਲਿਆ ਹੈ। ਕੀ ਤੁਸੀਂ ਇਹ ਜਾਣਦੇ ਹੋ ਕਿ ਇਸ ਦਾ ਪ੍ਰੈਕਟੀਕਲ ਯੂਜ਼ ਕੀ ਹੋ ਸਕਦਾ ਹੈ ਤੇ ਅਸੀਂ ਇਸ ਨਾਲ ਅਨਨੋਨ ਟੈਂਪਰੇਚਰ ਵਾਲੇ ਆਬਜੈਕਟਸ ਦੇ ਟੈਂਪਰੇਚਰ ਪਤਾ ਕਿਸ ਤਰ੍ਹਾਂ ਲਾ ਸਕਦੇ ਹਾਂ। ਚਲੋ ਤੁਹਾਨੂੰ ਅਨਨੋਨ ਟੈਂਪਰੇਚਰ ਵਾਲੇ ਪਲੈਟੀਨਮ ਵਾਇਰ ਦਾ ਉਦਾਹਰਣ ਲੈ ਕੇ ਇਸ ਦਾ temperature calculate ਕਰਨਾ ਸਿਖਾਉਂਦੇ ਹਾਂ। We will take a platinum wire about 50 centimeter in length and wind it on non-conducting rod with non-inductive winding. Connect this platinum wire in the arm CD of Wheatstone bridge circuit. Make the connections as this diagram shows. Let me first tell you the working and then explain the theory behind this working. First of all, keep the platinum wire S in ice at 0 degrees Celsius. Make P equal to Q and adjust the value of R so that on closing key K1 first and K2 later on, galvanometer shows no deflection. That is, the bridge is balanced. If R0 is the resistance of platinum wire at 0 degrees Celsius, then P upon Q is equal to R upon R0, or R0 can be written as equal to RQ upon P. Let us name this equation as equation 5. Now, keep the platinum wire into steam at 100 degrees Celsius and repeat the experiment. Let R dash be the resistance of the arm AD for which the bridge is balanced. If R100 be the resistance of platinum wire at 100 degrees Celsius, then P upon Q is equal to R dash upon R100, or R100 can be written as equal to R dash Q upon P. We will call this as equation 6. After this, we keep the platinum wire into the bath whose temperature T degrees Celsius is to be determined. Repeat the experiment again. Let R double dash be the resistance of arm AD for which the bridge is balanced. If RT be the resistance of platinum wire at T degrees Celsius, then P upon Q is equal to R double dash upon RT, or RT can be written as equal to R double dash into Q upon P. Let this be equation number 7. If alpha be the temperature coefficient of resistance of platinum wire, then R100 is equal to R0 into 1 plus alpha into 100, or alpha is equal to R100 minus R0 upon R0 into 100. This becomes equation number 8. Also, RT is equal to R0 into 1 plus alpha multiplied by T, or alpha is equal to RT minus R0 upon R0 into T. This is equation 9. From equations 8 and 9, we have RT minus R0 upon R0 into T equal to R100 minus R0 upon R0 into 100, or T is equal to RT minus R0 upon R100 minus R0 into 100. Using equations 5, 6 and 7, the expression for T can also be written as R double dash minus R upon R dash minus R into 100. So, I believe you have understood now how to determine the unknown temperatures. As you know, we are studying the Kirchhoff's laws and their applications today. Let me introduce another application after the Wheatstone bridge. This is called the slide wire bridge. A slide wire bridge is a practical form of Wheatstone bridge and is commonly known as meter bridge also. For obvious reasons, the principle of working of a slide wire bridge is just the same as that of a Wheatstone bridge. It consists of a wire AC of constant tan or manganese of 1 meter length and of a uniform area of cross section. It is stretched between the copper strips on a horizontal wooden board. a meter scale is also fitted on the wooden board parallel to the length of the wire. There is another copper strip fitted on the wooden board in order to provide two gaps in strips. Across one gap, a resistance box R, and in another gap, the unknown resistance S are connected. A jockey B is made to slide on the bridge wire. One terminal of the sensitive galvanometer G is connected to jockey B and the other to the terminal D. The positive pole of the battery E is connected to terminal A and the negative pole of the battery to terminal C through a one-way key K. Can you notice the circuit is just like that of a Wheatstone bridge? To get the slide wire bridge working, you have to start with closing the key K and adjusting the resistance box for a suitable resistance R. Then adjust the position of jockey on the wire, say at B, where on pressing galvanometer shows no deflection. Note the length AB, say equal to L of the wire. Also note the length BC, which is equal to 100 minus L of the wire. The bridge is balanced now. Therefore, according to Wheatstone bridge principle, P by Q equal to R by S. Here, P is proportional to the length L of the wire, or P is equal to L into R. Q is proportional to the resistance of the length 100 minus L of the wire, or is equal to 100 minus L into R. Thus, we can say LR upon 100 minus L into R is equal to capital R upon S, where small r is the resistance per centimeter length of wire, or S is equal to 100 minus L upon L whole into R. Now, if we know the values of the length of the wire L and the resistance R, the value of S can be calculated. There are some interesting facts about a slide wire bridge or a meter bridge that I must share with you all. First of all, let me tell you that a meter bridge or slide wire bridge is the practical form of Wheatstone bridge. Secondly, the Wheatstone bridge is sensitive to its maximum when the resistance of all the four arms of the bridge is the same. Then, the meter bridge cannot be used to measure very high or very low resistances. And after all, the balanced position of meter bridge is not affected on interchanging the positions of battery and galvanometer. Kirchhoff's laws ਦੀਆਂ ਕੁਝ ਹੋਰ ਐਪਲੀਕੇਸ਼ਨਸ ਵੀ ਹਨ ਜਿਨ੍ਹਾਂ ਨੂੰ ਡਿਸਕਸ ਕਰਨ ਲਈ ਸਮਾਂ ਅੱਜ ਆਗਿਆ ਨਹੀਂ ਦੇ ਰਿਹਾ। ਅੱਜ ਇਸ ਪਾਠ ਦੇ ਇੰਪੋਰਟੈਂਟ ਐਸਪੈਕਟਸ ਇੱਕ ਵਾਰੀ ਦੁਹਰਾ ਕੇ ਇੱਥੇ ਹੀ ਸਮਾਪਤੀ ਕਰਦੇ ਹਾਂ। Kirchhoff's first law or Kirchhoff's junction law states that algebraic sum of the currents meeting at a junction in a closed circuit is 0. The second law of Kirchhoff, also called the Kirchhoff's loops law, states that the algebraic sum of changes in potential around any closed path of electric circuit or a closed loop involving resistors and cells in the loop is 0. That is, sigma delta V is equal to 0. It means that according to Kirchhoff's second law, in a closed loop, the algebraic sum of the EMFs and algebraic sum of the products of current and resistance in various arms of the loop is 0. A Wheatstone bridge is a practical application of Kirchhoff's law. The principle of Wheatstone bridge states that if four resistances P, Q, R and S are arranged to form a bridge as shown in this figure with a cell E and a one-way key K1 between the points A and C and a galvanometer G and tapping key K2 between the points B and D. On closing K1 first and K2 later on, if galvanometer shows no deflection, then bridge is balanced. In that case, P upon Q is equal to R upon S. A Wheatstone bridge can be used to determine unknown temperatures of devices. A slide wire bridge or a meter bridge is a practical form of Wheatstone bridge. This is generally used to determine the resistance value of an unknown resistor. It is now time to test your understanding of today's lesson. Let me ask you some questions to make you more confident of this understanding. The first question of today is, state the Kirchhoff's first law. Answer. It states that the algebraic sum of the current meeting at a junction in a closed circuit is 0. The second question is, mainly which law of Kirchhoff is used in a Wheatstone bridge? The answer is, Kirchhoff's second law is used in a Wheatstone bridge. I am sure, students, that you all enjoyed learning Kirchhoff's laws and their applications today. Thank you for attending the lesson with a good concentration. Goodbye and see you next time again with another topic.